Okay, so there's a lot of material that we covered in Chapter 7. Here's a little bit of a review just to kind of remind you of some of the things that we saw. This is by no means a comprehensive review of everything that we've seen, but these are, we're hitting a lot of the big topics here to remind you of what to study. If A and B are disjoint, so we're talking about sets here. The word disjoint means that their intersection is empty, so A intersect B would have to be the empty set. The number of elements in their intersection would have to then be 0. The union rule for sets says if I take the number of elements in the union of two sets is equal to the number of elements in the first set plus the number of elements in the second set minus the number of elements in their intersection. And of course, this is a formula. You could rearrange it using algebra if it suits you. Obviously, there's more things we saw with sets. We talked about intersections and unions and complements and that sort of stuff. We also talked about Venn diagrams. So obviously there's more information, but these are some of the formulas that we have seen. Let's see, when we're talking about basic probabilities, the probability of an event, if you know that S is the sample space of equally likely outcomes, then you can say the number of outcomes in the event divided by the number of outcomes in your sample space gives you the probability of that event. We always know that the probability of an event is between 0 and 1. This would be inclusive. You could have something with exactly 0 probability or a probability exactly 1. That works just fine. The sum of all distinct outcomes. If you talk about, this doesn't depend on them being equally likely outcomes, but if you looked at all distinct possible outcomes, they would have to sum up to 1. So if you look at, think of this as a Venn diagram. If you looked at the probability of this region plus the probability of this region plus the probability of that region plus the probability of that region, all of those would have to sum up to 1. All right, mutually exclusive events. This is the vocabulary we use to mean essentially disjoint events, but we call them mutually exclusive. I'm not sure why there's the change in language there, but it means the same thing. So if we have two events E and F, their intersection would have to be empty if they're mutually exclusive. That means the same thing. And the probability of the intersection there would then have to be 0. The union rule for probabilities looks almost identical to the union rule of sets, except it's dealing with probabilities instead. So the probability of the union of two events is equal to the probability of the first plus the probability of the second minus the probability of their intersection. The complement rule says if we're trying to find the complement, the probability of something's complement, we can just take 1 minus the probability of that thing. So the probability of E complement is 1 minus the probability of E. Another way of saying that is that the probability of an event plus the probability of its complement are equal to 1. We did briefly see odds. If the odds of an event are n to m, then we can come up with the probability of the event. It's just n over n plus m. If the probability of the event is if we're going from the odds to a probability. If we want to go from the probability to the odds, what we'd do is we'd say, okay, we take the probability of the event divided by the probability of its complement. Or another way, if we actually have the sample space of equally likely outcomes, we can do n of E divided by n of E complement as well. Oftentimes we don't actually have the sample space of equally likely events, though, so that's when we have to kind of revert to the probability, although you can use the probability in either case. Conditional probabilities. This is when we have these given statements, so E given F, the probability of E given F. Whenever we see the probability of something like this, it's always the probability of their intersection divided by the probability of the condition. This is if we're actually looking for a formula. Oftentimes when we first started this stuff, we didn't really care about the formula so much. We more thought of the conditional probability as restricting our sample space. So instead of thinking of I mean, you could do it with probabilities. If you had the sample space of equally likely outcomes, you could also do it this way. N of E intersect F divided by N of F. This way really does look like restricting your sample space. Instead of your sample space being the entire Venn diagram, you kind of ignore all of this stuff. You say, okay, what happens if my sample space was just the stuff inside this circle? What's the probability of being within the intersection divided by the probability of just being in there, or the number of events total? Oh, yeah, that was that one right there. All right, the product rule of probability. This is what happens if we take that conditional probability formula right here and we multiply both sides by the probability of f. This gives us the probability of E given f rather, times the probability of f. Or you could do it the other way around. You could say the probability of f given E rather, times the probability of E. You know, they're interchangeable. These names don't really matter that much. They're more placeholders. But this one is pretty nice for finding the probability of the intersection, because oftentimes it's a lot easier. We can kind of think of what the conditional probabilities are based on that storytelling aspect, but the probability of an intersection can be more difficult. When we have independent events, let's give two equations that can be used. When we have independent events, then we can actually simplify this. Really what one of the formulas looks like is what happens when we take this product rule of probability. Oh, actually, before I get there, what one of the formulas is the conditional probability of f given E is just the probability of f. So if you're able to ignore the fact that that condition happened, that means you're dealing with independent events, and vice versa. And where the other formula comes from is if we then take this probability of E intersect f, which said the probability of f given E, but instead of the probability of f given E, since these are independent events, I'm just going to say the probability of f times the probability of E. So these are the two formulas we see when we're talking about independent events. You can say the probability of their intersection is the probability of the product of those two probabilities in each individually, or you can say you can ignore the conditional probability. The law of total probability is what we get when we have the tree diagram. And when we have a tree diagram, it actually doesn't matter how many branches it has. Let's say the event f happened here and here and here. You know, this would be maybe E1, E2, and E3. This would be f given E1, f given E2, and f given E3. And so ultimately, this branch here would be f. This branch here, when I multiplied those together, this would be f intersect E1, f intersect E2, and f intersect E3. What the law of total probability says is that if I take and I add the probability of these three branches together, that gives me the sum of these is equal to the probability of f. So I kind of go through here and I take all the branches where f happened, I add up all those probabilities that will sum up to the probability of f. This is just ways of writing it down in formulas, but really the way to understand it is with tree diagrams. And Bayes' theorem gives us a way of swapping around conditional probabilities. Really, it's using the probability of E given f. If this is the conditional probability we're after, we would use the probability of E intersect f divided by the probability of f. And so the probability of E intersect f would be, let's make this E1 so I can apply it to this example up here. The probability of E1 intersect f would be one of the branches. The probability of f we could get by finding these three branches and adding them together and using that law of total probability. So Bayes' theorem is just this process of kind of doing that. Now, in the book, there's big, ugly formulas that it uses. I don't really recommend trying to memorize those formulas. I think the way I've described it is a lot more elegant. You're a lot less likely to make a mistake if you think of it in terms of branches, and the branches where this event happens versus the ones that it doesn't happen.